So good morning, everybody. My name is Jeffro. I'm a program manager with the RISC-V International Organization. And I just wanted to go over the webinar very quickly. If you'll notice in the participant panel, you should be able to raise your hand. If you do that, I can reach you via chat. The chat window should be open as well. And you can also reach the Q&A box. That is a question and answer box. If you ask a question, we will see it pop up on our panels, and we can answer it at the time. Most of the presentations will save Q&A for the end, but go ahead and enter them in, and we can make sure that we queue them up so that we can get them answered. At this point, I will hand it over to Amir, our host.
Great, thank you, Jeffrey. So thank you all for joining this webinar in such a crazy time. This will be the second RISC-V meetup in Israel, hosted by Western Digital, UltraSoC and Codasip. And we'll discuss RISC-V debug and trace infrastructure, unique paging techniques, and SweRV Core support. It's a good opportunity to wish your family and colleagues health and well-being during these difficult times. We have an interesting agenda today, but to save time, I would like to introduce Ofer Shenhar from Western Digital that will present a ComRV cacheable overlay manager for RISC-V. Ofer?
Yep, it's good.
Excellent. Okay. Good evening. Good morning, everyone. My name is Ofer Shenhar. I'm working for Western Digital at the Department of Next Generation Platform Technologies under the CTO. And today I want to present you a feature that we are developing. It's called the Cacheable Overlay Manager for RISC-V. In short, it's ComRV. Basically, it's a technique for paging in software, and I will present that today. So on the agenda, I'm going to introduce some solving code space limitation with this technique, the basic concept and use cases for it, the building blocks that we needed in order to make this happen, the changes in the toolchain, and the deployment for this tool. So let's start with the introduction. So in the early days of embedded computing, there was the technique to load code on real time when it was needed to be executed and replace it after it. We can actually spot a few examples in the early days of computing by NASA, which they use the early shuttle flight control system to replace the code from launch sequence into an orbit sequence. And this technique was called overlay. It gives an easy interface to the software engineer to write his code, and without any need for complex other IPs like MMU or things like that. And it was threaded with the toolchain and the firmware itself. Today, IoT devices have the same memory, and it's without MMU, or most of them don't have an MMU due to the size for the IoT devices. And the need for code space for those devices alongside RISC-V code density challenges revives the needs for the overlay technique. Let's look on some basic concepts. Okay, so in the middle here, we can see the software model, which will execute it on a fast RAM, and it will decide what to load from the slow storage on the right into the fast memory area, which we called the cache area. Any slow memory can be fit. It can be even a TCP/IP protocol. The engine itself don't care. It just provides a hook for the user to provide the slow memory interface. The router module itself will also manage the cache itself. It will invoke the overlay calls, and it will ask what is needed to be loaded and what needs to be evicted from the fast memory. let's look at some user usage. So here we can see like a very simple example of two functions. There is bar and there is foo, and foo is calling bar. On the toolchain side, we're going to see something like that. There's going to be a jump to bar when it's needed by its symbol. And this is how it's going to look on RISC-V when using cacheable over manager. So the user only needs to add.
Ma?
Amir, you're not on mute. Okay. So the user only needs to add an attribute saying overlay to bar function, and that's it. From this moment, bar is just an overlay function, and the user, this is all the new user needs to do. Foo is calling bar and this attribute. Underneath, what's happening is that the toolchain itself will generate a few things. First of all, it's going to be generate a token, a descriptor for a bar function, and then it's going to jump to the engine itself, the ComRV engine, with this token, in order for the engine itself to understand what needs to be done with this function. If it needs to be loaded, if it's already loaded, maybe you just need to jump to it, etc. It's also important to remember that once we are inside an overlay function, all the callers and callee for overlay will need to go inside the overlay function, the overlay engine, sorry. That's because when your caller is an overlay and your callee is an overlay, and you're coming back from the callee, you want to make sure that the caller is still there. So you need to go to the engine, and the engine will decide if the caller is there, and if it's not, it's going to load it back. Since we are loading from a low-speed storage, we want to load as much functions as we can in just one shot. This means we need grouping. We need to group functions together. So overlay group is a container for functions and a read-only data. And the overlay itself, the engine itself, the runtime module is loading groups. It's not loading functions, it's going to load groups. Each group can be on the size of half a K to 4K, 4K, and it can be configurable on a compilation switch before running the code itself. So it just makes sense to gather functions together, right, to one group. So we have to provide some capability to do this. So we provide two modules to make this happen. We call this one we call manually, and the other we call automatically. Well, grouping manually means that the user knows which function goes with what. For example, inside the code, you have spike code with many functions, and you have RISC-V code with other functions, encoding, decoding, etc. So the user knows he wants to put all the spike code in the same group, and all the RISC-V code in a different group. So we provide kind of a utility to do this. It's very simple, very plain text file, which the user just needs to register his functions to the group, and that's it. Another technique is an automatically, where the user don't want to understand or don't want to choose what to load and what not. You want something to do this for him. So there is a tool that the linker can invoke on link time to make the decision of what is the best grouping options for this software flow. In order to do this, the user needs to provide a profiler file for all the overlay functions. I will talk later that on maybe I think on the last slide, explaining a little bit about this technique. And of course, you have another option that you don't want to use grouping at all. If you don't care about performance and you don't care about loading functions altogether, then you just don't say that you want grouping. And by that, each function will be in its own group. Another feature, which is a very unique feature, we call it a multi-group. I will try to explain that by showing an example. So sometimes different software scenarios can run the same function. So let's look on the example. Let's say we have a cache area that can fit only one group. And we have my foo function in group A, and it's been used by function 42, meaning function 42 calling it. And it's also needed by function 1003, which is in group B. This means we need to evict A when B is running, and back to A when we call my foo function for function 1003. This means a lot of flipping between paging, right? Between groups. A lot of flipping, which means it's going to take a lot of time. So multi-groups will give us the option to put my foo function both in group A and in group B. And therefore, we don't need to flip between them on different scenarios. Let's look a little bit above and look about the logic flow. So the overlay function will pass through ComRV runtime engine. The engine is written in C in assembly, and that is why it's rated with RISC-V target. And it can only work on RISC-V targets. The main engine workload is to load or evict overlay functions from the cache. It also have evict algorithm based on cache concepts like an LRU. And we also contain a fragmentation algorithm in order to close the gaps and holes when we evict several groups from the cache area. So just this is very high level. This presentation we can share later, so you can watch it all. Okay, so let's look about the building blocks that we need to modify in order to have this magic happen. So as the compiler, we choose the LVM and the Clang. The compiler creates special calls for the overlay function and is responsible to jump to the engine. For the linker, we choose the LD by GNU. It creates the descriptors, the tokens for functions, and the offset tables for the overlay functions and the overlay groups, for the multi-groups. As a debugger, we choose the GDB. It provides an easy interface to the user for debugging an overlay function and an overlay call. For example, if you want to put a breakpoint inside an overlay function which is not loaded yet, you can have this option just normally by debugging it. And if you want to do a step into a function of on overlay, you don't want to see the engine itself. You just want to go directly into your function. Therefore, all those changes in GDB. We provide other utilities like grouping tool, some extensions from the map file, and other service utilities that goes all together in the binutils. So I want to share with you now one of the utilities we provided with the toolchain, the grouping tool that I mentioned earlier. And I want to a little bit explain how it works or how it's going to work. So here we can see an histogram, which is based on time. Each bar here represents a function, an overlay function. So for example, orange is a function and blue is a function also, is a function also. And we can see that around this time, this function was called 12 times, and this function was called 10 times. Sorry, the same function was called 10 times. So if you're giving it names, so this is like the initialization stage, and this is the first steady state. So what we want to see kind of an algorithm that's define and split or find the hot activities for all of our functions. After we can split those areas, we can start merging it to groups. So let's a little bit dive into it. So let's assume what we need to do is to split each function with its own histogram. So we have function A, function B, and function C. Like you see here, the brown, the blue, and the green. And we have an histogram for each one of them. So we can see the result of activities in function A at the beginning of time, same for B, and green is a little bit after it. So after we spotted those areas, we spotted the hot activities, we can now merge those histograms into one. So we can see that blue and brown come together. So the recommendation will be to start grouping blue and brown together. And green is by itself. If there is a room on the first group, then we can push also green one. Then we can save some loading time. But if not, then green will just be in its own group. So as we saw earlier, this is like the initialization stage. And this is like the steady state. Okay, so now for deployment. So how we can access to ComRV? Well, that's the easiest answer. It's open source. So I invite you everyone to just get in touch in GitHub from RISC and Digital, and it's there and you can start using it. It's designed to fit bare metal software and with RTOS-based software. Currently supporting FreeRTOS on this phase, but we can port it to different operation systems. It's not a lot of tasks. It's not so hard to just port it to others. Currently, it's fully deployed with all the toolchain support. We are still on integration issues, but it's all there. So you can have it already built for Debian system in our GitHub, or you can have the source code itself and build it by yourself. Following next, we're going to make some more demos, more usage for each ComRV API. We believe that this will give us more stable SDK for user to use, and therefore they can just prepare and design their new software projects based on ComRV. So as much demos we can provide, we think everyone will enjoy it. And this is the link for our repository that holds all the engine and also the build toolchain. That's it. Thank you very much. I will look into questions now. So first question was the overlay purpose of ComRV is to load code from Flash into DRAM or SRAM as needed. So the answer is yes. You can load it from Flash, but it's not necessary from Flash. You can load from any storage. Another question. There was a question about functions calls from ISR. So it's a good question. We are not supporting using of overlay from ISR. So that's one of the restrictions. You cannot call overlay functions, or you cannot put interrupt handlers as an overlay. So that's something we don't support. Another question is, can we run ComRV on FPGA? So it's a good question. ComRV is agnostic to hardware, so it can actually run on any target. As long as it's RISC-V, it can run on FPGA, on ASIC, on simulation, on ISS, on any tool. But on our repository, which I share with you, you have a firmware infrastructure that have a few platforms, including simulators and including FPGA that we got from Chip Alliance by Olaf. So it's working on that, and it's working on the ISS, and it's very cool. Another question just popped in. What RISC-V extensions are required? So you just need the basic one, the I and the M. And actually, it can also work just with I. Okay, another question. What kind of security verification tools are you using for RTL simulation? So this is actually a question for FPGA and hardware guys, because this is pure software. So sorry, but I don't have the answer for that. Any other questions? It's very quiet. I hope that you can hear me.
Yes, we can.
Jeffrey, can anyone hear me?
Yes, we can hear you. I think that maybe there aren't any other questions. Can you post the GitHub link in the chat is one question.
Can you post the GitHub link into the chat?
Yeah, there's a
Yes, I can.
chat box.
Give me a second. Here you go.
The question is, are we going
Yes, I can share the presentation, no problem.
Yes, we'll get the presentation.
I will ask Jeffrey, the one that managed the current session, to share with everyone. No problem.
Yes, we'll get these posted on the RISC-V website after the event. Okay. If there's no other questions, Amir, do you want to take over?
Any more questions?
Thank you, Ofer. If there is no other questions, we can continue.
Yes, that's it.
Thanks, Ofer. We will now switch to Philip from Codasip, who will present SweRV Core commercial deployment support. Philip, can you upload the presentation?
Yes, thank you, Ofer, for the presentation. Just to make sure, can you all hear me clearly?
Yes.
Okay, that is good. I believe that you have to stop presenting so that I can start presenting my screen. Okay, now I can do it. Okay, good. You should see my screen now. Is it okay? Guys, can you see my screen?
Yes.
Good, good. So I'll start with the presentation. So hi, I'm Philip and I work at Codasip. And today I will present the SweRV support package, which is a support for commercial use of the open source cores from Western Digital. So let's start with the obvious explanation what the SweRV means. SweRV is the name of family of Western Digital processor cores. In this slide, you can see the roadmap of the cores. You can see that the first generation was introduced last year, containing one core, which is called EH1, and this year it is followed by two cores, one which is more powerful than EH1, called EH2, which introduces the double-threaded execution, and one which is focusing rather on the area by lowering the number of stages in the pipeline, and this is called EL2. So what is really interesting about these cores is that Western Digital has decided to open source these cores. The RTL of the H1 core is open sourced via the CHIPS Alliance, which is an organization which develops and hosts high quality open source IP. So if you want to, you can go to their GitHub page right now and you can download the RTL of the EH1 core. So well, Western Digital will give you the core, right? So is this everything that you need so that you can deploy this core in your chip? Well, this slide is trying to show that this process will be much complicated than that by showing you all the different processes that you will need to do during the deployment, from the software development to also the hardware development region. So you can see the compilation, synthesis, simulation, all the other different aspects. And I will be getting to this, this basically demonstration during my presentation. The deployment is not just about the RTL, as I mentioned, and this is why Western Digital partnered with Codasip to help users with the deployment of the core. And this is why Codasip provides the SweRV support package. And since we call it a package, let's start with the simple aspect, and which is what's inside the package. So the first area of focus is the software development. To enable the users to develop their software for the core, the package contains the GNU RISC-V toolchain, which we configured to produce the binary programs which will be compatible with the configuration of the RISC-V cores. For debugging purposes, we included the OpenOCD, which enables the users to perform the on-chip debugging. And so that the users don't have to do all their software development in command line interface, we also included the Eclipse IDE, which we extended with our custom plugin. The plugin generates the correct build settings for a C project, so that when you build the project, it will be built correctly for the SweRV core. And it also generates OpenOCD debugging configurations, which will enable you with a single click of button to load the compiled program into your FPGA board, run it or debug it, depending on what you want to do. The second area of focus is the hardware development. So the package includes a stable version of RTL designs. Obviously, it's the RTL of the EH1 core itself, but we also added an example of SoC which is based on EH1 called SweRV. We also include open source EDA tools and scripts which are related to a specific EDA tool and RTL design, which means that for simulation you would need a test bench, or for synthesis you would need timing constraints. Because the commercial development is usually or often maybe done with commercial tools, we also include these scripts designed for tools from leading vendors in the commercial area. So from what I just explained, it may give you the impression that what Codasip is offering is just an archive full of tools and scripts, right? But in the second part of my presentation, I will try to explain that this is actually not the case. The integration of these contents the integration of the contents is as important to us as the contents themselves. We adopted and extended an open source tool called FuseSoC, which serves as an integrated design flow in the support package. The FuseSoC has actually several functions inside the package, and I will explain them on this slide. It allows the user to specify their RTL project as something that FuseSoC calls a package. Each FuseSoC package can have dependencies on other FuseSoC RTL packages. So these packages may be either distributed with the support package. So for instance, we include a version of the SweRV EH1 core right inside the support package as it is, or these packages may also be provided in open source repositories in the internet. So this slide is trying to give you one of the examples where you can see that some of the peripherals packages are on the internet, and the core itself is inside of the support package. So when you provide the definition of your RTL package to FuseSoC, and this definition is here marked as the little file called mysoc, FuSoC will download all the necessary dependencies from their location. Then it will also add your additional source files that you have developed for this project. And this way it basically builds the RTL project in your workspace. Another functionality of FuSoC is that it can run EDA tools on any of the packages you have created. What is important is that the options which you need to run the EDA process that you want to run are specified in the definition of the FuSoC package. So you don't actually have to interact with the EDA tool itself. This way, FuSoC can provide these options to run different EDA processes, which are unified for tools from different vendors. So for instance, you have to specify some options and arguments to run an RTL simulation. Then you specify what tool you want to use for the simulation. And in the background, FuSoC will translate all these arguments and options into the very specific options of the RTL simulator that you have chosen and run the simulation for you. That means that if you, for instance, decide to test a new implementation of the simulator from a different vendor, for instance, and you already have the whole simulation process specified in the FuSoC project, the only thing that you basically have to do is to change the name of the simulator that you want to use. And FuSoC will start translating your settings into the specific settings of the different simulator that you decided to use. And you don't then have to rewrite the complete infrastructure of scripts that you might use if you do not use FuSoC. So providing the mentioned software and other contents, it could raise a problem of the dependencies that the user would have to take care of, and we didn't want it to happen. So this is why the whole support package is provided as a Docker container with all the dependencies pre-installed. Since Docker container is a lightweight Linux environment running inside a host machine, we were aware of the fact that the users might be afraid that some of the activities that they do during the development on their host machine would not be functioning inside the Docker container. So we made sure that the following tasks could be done. Among these is the ability to connect a development board via USB to the container. You can also run graphical applications from the container. So if you start Eclipse, for instance, a window will pop up with the Eclipse and you can start developing your software in Eclipse. And if you want to mount some drives into your Docker container, because for instance, you keep your work on network drive, this is also possible. So now let me explain the different versions of the support package that Codasip is providing. So here we are back to the slide that I basically started with. And this time there is this distinction by color of the different aspects of the deployment process. And this is basically dividing the two different versions of the support package that Codasip provides. So let me discuss these two versions in more detail in the following slides. So the free version, the first one, we basically think that everything that is originally open source should stay free for the users. So all the software development tools which are currently from open source projects will be part of the free version. Also, the integration for open source EDA tools into the FuSoC design flow will be part of the free version, and documentation and examples will be also part of this version. If you need any help while using the free version of the SweRV support package, you may reach it via the dedicated discussion forum. And we're basically aiming on students and educational purposes with this version of the support package. We will also provide a pro version of the support package, which contains everything which is part of the free version, but it also adds the integration of commercial EDA tools into the FuSoC design flow and all the additional scripts that are usually part of the various design flow processes. Currently, we support tools for static analysis. We support RTO simulation, synthesis, and equivalence checking. And what is really important is that the part of the Pro version will be a personal support for the customers. So if they have any, they need any help during their design efforts, or they have problem using the support package, they can reach help over support tickets, phone calls, or possibly also on-site visits if that is necessary. So additional services that Codasip can provide. The main business Codasip is doing is specializing on core design and customization. So it makes only sense that we will also be able to provide customization of the SweRV cores for our users. So if the user, for instance, needs to add a floating point unit or bit manipulation instructions, and they cannot do it themselves, it can be done as a service by Codasip. Codasip is also currently working on introducing verification as service. So once this is finished, we will definitely announce this. And this brings me to the summary of the presentation. The main purpose of the support package is to make the deployment of this open source SweRV Core simple and fast. We're making the whole process simpler by using the design flow, which enables support for multiple EDA tools, and by also providing the environment which will not require the user to install different dependencies, so the start is really fast. We also provide comprehensive documentation also for the open source tools, so everything is on one place and you can learn how to start using the tool right from the support package. What is really important is that all the contents of the package are tested by Codasip, and since we're using also some open source content, it may happen that time to time the latest version of the tool is not working properly, and in this situation we will not release this version to our customers, and we will stay on the last stable version and try to find a solution how to solve the problem that arose. The users of the Pro version will also have access to personal support, which in commercial development will be very important because it helps them with the usage of the SweRV support package, but also with the problems related to their design efforts. And as I mentioned at the end of the presentation, Codasip is also offering a customization and verification as additional services to the support package. So this is it from the presentation. I included a link to GitHub where you can get the free version of the package. However, if you go to our website, codasip.com, there will be more information on the package included, including the link and access to the forum, so you can access all of that. If you have any additional questions, feel free to ask. I will check how many questions are there, and also if someone already or my colleague already answered some of them possibly. Just to make sure, can you still hear me?
Yes, we can.
Because I had some problem with Zoom. It's somehow, yeah, I think that I'm back to my presentation now. So I will open the Q&A box. Will you be supporting the upcoming EL2 and EH2 cores too? Yes, we will. We are already looking into the EH2 core, and we will be working on the EL2 core as well. Yes, it requires some additional work. So in the initial release that we're releasing now, we have the support for the EH1, but these cores will be supported as well. So I don't see any other questions.
Okay. Thank you, Philip. This was very interesting.
You're welcome.
And we are on time.
Oh, are there any open source tools for RTL synthesis supported by RISC-V designs? Well, this could be a general question, so then I will say rather that I'm not sure. If it's related to the SweRV support package, then the answer is no. Okay. Okay, if that's it, then thank you, and I'll leave the presentation to the next speaker.
Thank you, Philip. So I would like now to introduce Hanan Muller from UltraSoC, who will present the UltraSoC debug and trace infrastructure for RISC-V. Hanan, are you ready?
Yes, I am. Can you hear me okay, everybody? Or those who can respond anyway.
Yeah, we
Hello?
see the presentation.
Ofer, Amir, can you hear me okay?
Yes, and we can see the
Okay.
presentation.
Great, okay. Thank you very much, everybody, for joining. It's a pleasure to be here under those circumstances. It would have been much more fun to come and visit in person, maybe something to look forward to in the hopefully not too distant future. As Amir said, my name is Hanan Muller. I work for UltraSoC, leading the application team for the company. And today we want to talk a little bit about some debug and particularly trace infrastructure for RISC-V based SoCs. Right. We will talk a little bit, quick overview, talk about instruction trace, cycle accurate instruction trace, and then time permitting, we'll tell you a little bit more about some of the work that we are doing at UltraSoC to help with SoC debug and analysis, not necessarily just around RISC-V cores, but SoC overall. Excuse me. So we maintain that we're all building fairly complex systems, and just by the name, the issue is with the system. It's not just about the ISA, as important as it is, and not just about the core, as complex and exciting as it may be. We need to address the system complexity, the interactions between different cores, between software and the cores, real-time events that are happening. We write software, we spend a lot of time debugging software, but rather surprisingly, the software doesn't behave quite in the way we expected it to. And there were some studies that were done, I guess it's 18 years ago, that show that between 50 and 75% of the time is done debugging software. It's probably not gotten much better, given that compute resources are so much more readily available, and we're trying to solve problems which are much more complicated. So increasingly, the real-time performance, the safety and security of the system are increasingly important and must be dealt with. So there are multiple approaches, many different approaches to doing that, different methodologies, but one of them, the one that we want to talk about today, is providing non-intrusive visibility in such systems. I think the requirement to have non-intrusive visibility is crucial. Once you start stopping your program to observe what's happening in the system, then the behavior of the system changes completely. And then when you stop observing it, all of a sudden, so you know, you try to debug something, everything looks okay, and then when you remove all your printfs and this and that, things start behaving badly again. So we want to be able to observe the behavior of the system without being intrusive at all. And one of the two methods that we're going to talk about are processor branch trace, which can provide a good visibility into the program behavior, but we maintain that in some cases this is by itself not enough. We also need to understand the times when processors are stalling and then try to understand why they are stalling. So we want to spend the next few minutes talking about the RISC-V standardized instruction trace. The idea behind processor branch trace is that you want to start from a known address and then communicate the deltas that the program is taking. So normally, I guess the program is just continuing linearly until it hits a branch or a jump instruction or text an exception, at which point it goes to a different PC. So we mentioned a few of those reasons for those deltas, and with all of that in mind, we then need to, once we know where we started from, we only need to report, or the trace only needs to report that there were changes in flow, so when we hit an instruction that can branch or maybe continues, we need to report whether or not this branch was taken, but we don't, for many of those branches, there's no need to report the address that we went to, because the branch address can be inferred from the execution binary. In other cases, such as indirect branches or jumps, we don't necessarily know the destination address statically, so the report in the trace needs to take that information into account and communicate that address. We need to worry about interrupts and exceptions as well. Interrupts generally occur asynchronously, so we don't really know when they're going to happen. They're just coming sort of out of the blue from a program progression point of view, and somewhat similarly exceptions, although exceptions are normally not triggered by hardware events, but rather by specific instructions. So I guess, for example, if there's a floating point instruction that's running on a core that does not support that, there will be an exception, and the handler will deal with that. So the processor trace encoder must take care of that and report the information as needed, so that the software decoder that's running in the debugger will be able to retrieve and reconstruct the program flow. So when we say standardized processor trace, the RISC-V Foundation had recently ratified the processor trace specification, and within that specification there are two main parts. The first part is defining the hardware interface between the CPU core, such as, for example, SweRV, and a trace encoder IP. The information that is being communicated on that interface is for every instruction that is being retired, there's an indication that an instruction had retired, the type of instruction. So for example, a load and store instruction needs to be recorded or needs to be communicated. The fact that it retired needs to be communicated, but the encoder doesn't really do anything significant with it because it does not change the program flow. However, a branch instruction needs to be looked at and reported as either a taken branch or a non-taken branch. So those two first fields take care of that. The instruction address, again, so that the encoder can track where the program is, and then there are additional fields that have to do with exceptions and privilege modes and so on. In terms of the overall flow, the CPU core obviously is going to be running whatever workload it is running. The trace interface will report retired instructions. The trace encoder will collect this information and form what is referred to as trace packets. We will see what those contain in a few minutes. Then there's some SoC level debug infrastructure that will communicate that trace to trace decode software that will then take those trace packets, have access to the execution binary, so typically an ELF file or something similar, and be able to generate, let's say, a disassembly listing of the program as it was running. There are some additional sideband signals that can be used that the standard supports, and it is, as we mentioned, it is now a RISC-V standard. The link to that standard will be shown in a little bit. There are some additional interfaces that are optional, or additional signals which are optional to support better efficiency for multi-retirement CPUs. We're not going to get into the details of that, but when I mention, when I talk about efficiency, it is all about creating an efficient encoding within the trace encoder, and to be able to communicate the trace information with as many, as few bits as possible that need to be pushed off chip, because obviously the lower the bit bandwidth in here is, the simpler the debug infrastructure is and the interfaces to go off chip. So the trace encoder outputs trace packets, and there's a number of different packet types being defined, but predominantly the efficiency savings come from having a branch map. So for every branch instruction, we need to capture a single bit in the branch map, basically to say, was this branch taken or was it not taken, and that's it. So if for example, you sit in a loop that is just using branches, you know, I don't know how many instructions will be in that loop, but if this loop, for example, iterates 32 times, and within each iteration, let's say you execute 20 instructions, then those 30 iterations of 20 instructions will take roughly 30 bits in a branch map. There's additional information that need to potentially be included with an update trace packet, which is when we have change of flow that does not that requires specifying the new address. There are options for having differential address, which can be encoded in a fewer number of bits. If you jumped 120 bytes away, you can obviously encode it in fewer bits, or if you do a long jump to the other side of the world and you encode it with the full address, again, all to achieve better efficiency. The instruction trace specification includes the instruction trace algorithm. We will show the slides later. We're not going to have time to go into the details in here, and it's probably a little bit too small to see in here anyway. But and here is the spec lives in GitHub under the RISC-V section in there. Just wanted to share a few benchmark results that we have seen. So we're running different programs, many of, or at least some of which are part of the Spike set of benchmarks, and the numbers, the BPI, the bits per instruction, show the efficiency of the trace encoding algorithm. So if we look at, for example, QSort in the middle in there, we run that benchmark with trace, and we count how many bytes or bits of trace are coming out, divide the number of instructions by that, or the other way around rather, and we get, let's say, about a quarter of trace bit per retired instruction. Clearly, you can see here that the numbers will vary quite a lot. It all obviously, like many software things, depends on how the software is written and the flow behavior therein. On top of being able to create trace, you want to be able to control when the trace is generated. You may not wish to trace every instruction that's happening. You might want to only focus on specific types of particular functions within your code, or only maybe trace when inside an ISR, etc. So to support that, there are filtering mechanisms which our trace encoder IP supports. They're not explicitly a part of the standard. I think the standard talks about filters, but does not specify how to create them and how to manage them. So as I mentioned, our trace encoder IP supports filtering to filter trace within a specific address range, particular privilege levels, interrupt service routines over a particular period of time, start or stop trace when some system level event is detected, and so on. And the reason for wanting to do that, again, is to help improve the life of the person who's doing the debug, trying to focus only on the areas that require debugging and not on the stuff that's not interesting. We also now want to talk a little bit about a cycle accurate instruction trace using what is called retirement delta trace. This is not part of the RISC-V processor trace standard. This is an add-on that our trace encoder IP supports. And the idea in here is the objective of retirement delta trace is to be able to determine when is it time-wise that each instruction retires, but more importantly, identify CPU stalls and the length, the time between retirements. So to do that, we report the number of clock cycles between each successive retirement. Now, hopefully, our caches are great. We're not doing, there are no misses. So most of the time, we will retire an instruction every single cycle, or even better in a multi-issue machine. So rather than, again, in terms of efficiency, rather than report, okay, you know, there was one clock cycle, we retired another instruction, retired another instruction. We want to be more efficient and say, okay, we retired, let's say, 20 instructions consecutively. It will be much, the encoding for that will be more efficient. So the basic reporting unit or reporting group for the retirement trace will be two numbers: how many contiguous retirements had occurred, and then how many stall cycles followed. In cases where we have CPUs that support multiple retirements, need to be able to report also how many instructions retired on a particular cycle, because even though you may have, let's say, if it's a 4-issue machine, it does not mean that all 4 pipelines were retiring at the same cycle. So we need to be able to report that as well. So the key to the efficiency in there is the encoding format, and the encoding format that we've implemented is something called Elias Delta. There's a link at the bottom there to showing some of the efficiencies, and I think that what we want to do next is just mention that we then discuss, or we think we define 5 different token types, A through E, and each one of them, each token is then an Elias gamma delta, Elias gamma encoded count of something, and then we pair tokens together in groups to achieve efficient packing. We have quite a few slides showing those very detailed examples. I don't think we're going to have time to do this, and it's probably something that requires a little bit more interaction, and given the medium, it's a bit difficult, but let's just try to do the first one here, so that we can show the example, and then you can at your own time look at the others, and if you have any questions, please reach out, and we're going to be more than happy to discuss that. Let's assume for a moment that here's a set of clock cycles where a single retirement heart. So here are 4 clock cycles, where instructions were retired, then we stalled for a cycle, we retired for 3 cycles, and so on. So the encoder will look at that and say, okay, I've seen 4 retired instructions. Token A counts that. Token C counts how many stall cycles there were, and encoding this requires 6 bits. Then the next group is going to be similar behavior with obviously different numbers. And then if we look at the next group over here, group number 3, we had 2 retirements and then 4 stalls. So that gets reported in one group with those values in here. And we can see that for this sequence we had 18 bits with however many 9 instructions altogether. So we get this average number in here. I think I only have about 5 or 10 minutes left. Let's just do one more example in here. So for the same sequence of instructions, we can get a better, we can trade off the efficiency for accuracy by amortizing the stalls. So then we look in here at all of this entire group, and we we can see that altogether we retired 1, 2, 3, 4. The way the tokens are calculated, we needed 13 bits in total. So so I think that there are 12 cycles altogether. With token B says how many. Token B says how many missed retirement opportunities there are altogether. So we missed opportunities in here, and then 3 stalls at the end. So altogether, we can see for the same sequence of instructions that we're more efficient in terms of bits per instruction, but obviously we don't have the visibility into precisely where those stalls occurred. So it's a trade-off, as I mentioned, between trace bandwidth and accuracy. I'm going to skip the others. There's an algorithm. The algorithm is shown in here. It's fairly straightforward. I'm sorry that we don't have enough time to cover this today. Putting next to the table that we've seen before, I know it's not an apples to apples comparison. It's not even apples to oranges comparison, but the retirement delta trace requires quite a bit more, as you can tell, quite a bit more trace bandwidth. But the numbers in here will really depend on, again, on the on the stall behavior of the program. This was obtained by running those different benchmarks with a certain stall probability, and which may be completely off, given that you know, we said that it's really great if we can get close to 1 instruction per cycle, but we're getting here CPI of 3, 4, 5. Then if the CPI was closer to 1, then those numbers will be lower. So it's really difficult to compare those numbers to anything. It's just to give a rough impression as to what's there. Right, the last few minutes that I have, I just want to briefly talk about some of the other work that we are doing over at UltraSoC. So we are providing IP that can help with monitoring the activity within the SoC. So if there's an SoC in here with whatever makeup of IPs, RISC-V cores, other commercial vendors, etc., we provide different monitoring IPs, so bus monitors that can look at, give very accurate trace and performance metrics of standard bus interfaces like AXI and CHI, status monitors to observe behavior in custom logic, debug infrastructure fabric to control and collect all the information, different communicators to allow debug software interact with the debug and analysis IP that we provide, and the SoC, instrumentation IP, trace and run control interfaces. So from say you're running a debug session, you're running a GDB over OpenOCD, and that talks through our hardware, through our those blocks in here, the PAMs, to the debug modules within the RISC-V cores or other processors, and enable to do the standard type debug, single stepping, breakpoints, observing memory values, and so on. Some other IP to help with security and reliability for the entire SoC. So in summary, we are building systems which are getting more and more complicated every day, and our tool chains must advance and move forward with that. And one of the ways to do that is that we focus on today is detailed processor trace, including cycle accurate trace, alongside with a non-intrusive monitoring infrastructure with some of the other IPs that we provide, can give insights into the behavior of the system while it's running, as I mentioned, in a non-intrusive manner. I think that's all I have. Amir, I'm hoping I've not run over my allowed time. And if there are any questions, then we're going to be happy to take them.
I see there is 3 questions.
Right, let me see if I can find that. Right. So the first question I see is, how does this compare from Asaf Pollock? How does this compare to HTTPS GitHub? So I think that's the same one. Asaf, I know you can't speak back, but so the first question that's it's the same spec. Then there's a question from Siddiqui: is UltraSoC debug infrastructure embedded deep into the RISC-V processor pipeline? The answer is no. So the RISC-V, so our debug infrastructure is not embedded into the RISC-V processor pipeline. There are two, let's say, two interfaces through which our debug infrastructure talks to a RISC-V core. One is an interface to a debug module, and that's depending on the vendor, it's either something like JTAG or something like APB. And then there's a trace interface, which is a collection of signals that the processor vendor is responsible for bringing out to the boundary of the core, and to which we connect. Has UltraSoC debug and trace infrastructure for RISC-V? Sorry, how does UltraSoC debug and trace infrastructure for RISC-V compare to core site technology? That's a good question. I'm going to try and say that it's probably something that we can't do super quickly, so please reach out. We think that we believe that our technology scales better, provides more flexibility in terms of cross-triggering between different components within the system. Like I said, please reach out. The email address is what was shown earlier, and you can see it later. There was another question which seems to have disappeared, so I don't think I can answer that if it's no longer there.
Oh, I typed an answer to it. It was about the
you did. Okay.
We can just make a quick announcement that all those slides from today will be available later on the Meetups page on the RISC-V website.
So thank you very much.
Thank you, Hanan. Well, I would like to thank Jeffrey. Thank you very much for your wonderful support. And of course, the panelists for the interesting presentation. And everyone who joined the webinar, thank you very much. We are already working on the next meetup, hopefully with next month. And we'll of course update you all. And last, we want to wish you everyone health. Can you hear me?
Yes.
I can, yeah.
We want to wish everyone health, and we can only hope that the next meetup will be face-to-face and not virtual one. Good evening and good day, everyone.
Thank you very much, everybody, for coming.
Thank you.
Jeffrey,
Yes.
thank you very much for your support.
Oh, yeah,
Brilliant.
of course. Yes, of course. If you could make sure that I get the slides, I'll be sure to get them up. I think I've only got one so far.
Yeah, I think I set them last night, but if you still don't have them, I'll shoot them over your way again.
And I should have
Jeffrey,
video up.
much appreciated.
Sorry, hello? Who was that?
Amir,
Okay.
thank you so much.
Yeah, absolutely. Absolutely.
Amir, and thank you for hosting.
Sure.
Next time in Tel Aviv, maybe.
Looking forward to.
Or Petah Tikva. Are you in Petah Tikva?
Well, our
Kfar
office is
Saba.
in Kfar Saba, yeah,
Yeah, okay.
but any place you come in.
Yeah.
Thank
Okay,
you,
all right.
Amir.
I'm going to sign off now.
Okay.
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 Jeffrey,
Cheers. Bye-bye.
maybe in the Bay Area or in Tel Aviv someday.
Or in the UK. I'm based in the UK.
Yeah, I know. I was talking to Jeffrey.
Oh, I see. Sorry. So I didn't mean to invite myself into a meeting that's not mine. Sorry.
Definitely invite yourself. We'll meet up somewhere in the world.
Yep. Okie doke.
Take care, everybody.
Stay safe. Bye.
Okay, thank you, Amir. Thank you, Jeffrey. And can I just have a question? Where will the recording will be available on the Meetup page, or it will be sent over email, or?
Yeah, it'll be on the Meetup page, and I'll send the link over to Amir so he can post it to the Meetup group.
Okay, cool. Thank you.
You bet.
Thanks.
Have a nice day.
Yep. Bye, everybody.
Bye.
Bye-bye. Thanks.